In this chapter, we will introduce you to MPLS-TP. We'll define the differences between MPLS-TP and IP-MPLS, and then we'll go through the standards defining the main points of MPLS-TP. Finally, we'll review the highlights of additional capabilities provided in MPLS-TP over and above that found in IP-MPLS. In the Part 1 for the MPLS module, we covered the basic features of MPLS. We've described how IP-MPLS is actually MPLS riding on top of a Layer 3 infrastructure, where routing protocols such as BGP and OSPF are used to create and extend reachability information between all the nodes in the network so that protocols like RSVP and LDP can signal the LSPs for service reachability, and MBGP can be used for services like Layer 3 services to extend service reachability. This was all fine and good, but it was still very much enterprise focused and carrier network focused. It lacked a lot of the transport profile capabilities that were inherent and very relied upon in SONET SDH, OTN, and some of the TDM network structures. In February of 2009, a report on considerations for creation of a transport profile utilizing MPLS as a foundation was submitted as an RFC to the IETF, the Internet Engineering Task Force. This report was the initial proposal for cooperative development between the ITUT and the IETF for how MPLS could be applied as a technology for transport networks. Demands on MPLS forwarding capabilities were now being enhanced by requirements normally associated with transport networks. Some of those requirements included OEM, or Operations Administration and Management, control plane protocols, network management, and survivability. This would now drive an MPLS environment focused on connection-oriented packet switching. The end result of the MPLS-TP definition work is that MPLS-TP utilizes a substantial portion, but not all, of existing MPLS technology. This means that MPLS-TP will interoperate with existing MPLS infrastructures. If we look at the various components here, we see IP-MPLS overlap with MPLS-TP. The circle in the center shows the overlapping capabilities that are shared between IP-MPLS and MPLS-TP. We do a quick summary here to give you the high points in each area. In IP-MPLS, we see that it is still very much focused on control protocols, but it is very connectionless. There is no guaranteed determinism on where packets will flow, and it is very affected by the state of the network at any one point in time. Shared between both IP-MPLS and MPLS-TP is all the basic fundamental features of MPLS itself. That involves label switching, label allocation, and label distribution. So LSP and pseudo-wire forwarding is common to both MPLS technologies. Again, MPLS-TP is built on the base functionality of MPLS. MPLS-TP, well, the big thing there, and you'll see in the standards we'll describe in a few minutes, they emphasize the ability to require the ability to do static provisioning. So in other words, you don't have to use routing protocols to provision services, LSPs, etc. in an MPLS-TP or transport environment. The OEM in MPLS-TP is specifically aimed to be transport grade. We'll go through that. The services and LSPs in MPLS-TP, the LSPs themselves, they're deliberately meant to be connection-oriented. You are not allowed to have ECMP. ECMP means equal cost multipath. In IP-MPLS, you could, for example, build LSPs across multiple physical links to make use of the bandwidth and then do weighted round-robin across the links and paths. But that is not deterministic. There's no way to know which path or which link is being used for a packet at any one point in time. And that's not allowed in MPLS-TP. The next couple of slides describe the main differences between MPLS and MPLS-TP. In this slide, when we refer to MPLS, we are referring to IP-MPLS. The first difference is control plane dependency. In IP-MPLS, the data plane does rely on the control plane. MPLS-TP, no control plane is required, which means in times of failure and recovery, you do get fast convergence times and no dependencies under MPLS-TP. As a matter of fact, the MPLS-TP standards designate that the control and management planes must be physically separated from the data plane. LSPs in MPLS are unidirectional. There is an LSP for transmit and an LSP for receive between the two endpoints. Whereas in MPLS-TP, it introduces the concept of bidirectional paths, which means that the transmit and receive LSPs are actually associated to each other so that you know it is a transmit and receive pair between the two endpoints. They can be bidirectional co-routed or bidirectional associated. What that means is in bidirectional co-routed, the nodes used for the transmit path have the same nodes used for the receive path, so the two paths follow the same physical path. In bidirectional associated, the transmit and receive LSPs do not have to follow the same physical path. In IP-MPLS, ring support is not a mandated component, whereas in MPLS-TP, the standards specifically say that ring topologies must be supported. IP-MPLS is connectionless. Equal cost, multi-path scenarios are permitted in IP-MPLS, where these same scenarios are not permitted in MPLS-TP. MPLS-TP is specified to be a connection-oriented deterministic technology. Finally, IP-MPLS only has out-of-band OEM. So that means operations admin and management of services and LSPs must be done alongside out-of-band from the existing pseudo-wires and LSPs. Whereas now with MPLS-TP, it defines in-band OEM, which is fate shared. As an example, BFD, or bidirectional fault detection, has connectivity check and connectivity verification within BFD. BFD packets are actually associated specifically with and in the LSP or the pseudo-wire for the service. So you can actually now measure the actual service connectivity between endpoints, or the LSP connectivity between endpoints. Because MPLS-TP OEM is very similar to the transport capabilities of SONET SDH, it also includes frame loss measurement, LM, and delay measurement, DM. This slide focuses on the ring support requirement, and also 1+1 differences between MPLS and MPLS-TP. In MPLS-TP, 1+1 and 1-2-1 protection in a ring must support switching times within 50 milliseconds from the moment of fault detection in a network with a 16-node ring with less than 1,200 kilometers of fiber. In MPLS, this is all dependent on the interior gateway routing protocol, and it doesn't have the formal support for a ring. In the next several slides, we'll review the highlights of RFC 5654. RFC 5654 is the document produced by the cooperative efforts of the ITUT and the IETF in stating what must be present and what can be present to be qualified to be an MPLS transport profile. The first item is the MPLS-TP data plane must be a subset of the MPLS data plane, as defined by the IETF. This means basically that the MPLS-TP must be built on the core components of MPLS and must be interoperable with it. This next point goes through interoperability. It says that these MPLS-TP must be interoperable with existing MPLS services and control and data plane capabilities without requiring any kind of a gateway functionality, which is a translator that would be needed to interoperate between the two protocols. In other words, the MPLS-TP protocol must be effectively totally interoperable with the existing MPLS control plane and data plane protocols. MPLS-TP must be a connection-oriented packet switching technology and have traffic engineering capabilities, unlike IP-MPLS, which was not specifically required to be connection-oriented. MPLS-TP must support traffic-engineered point-to-point P2P and point-to-multipoint, so P2MP, transport paths. This is not equal cost multipoint, but specifically point-to-point and point-to-multipoint, which is still connection-oriented paths. This item describes the LSP features where they can support unidirectional, co-routed bidirectional, and associated bidirectional point-to-point transport paths for LSPs. Again, MPLS-TP is what brings in the bidirectional features. In this context, connection-oriented does drive the capability for determinism. MPLS-TP requires that the physical separation of the control and management planes from the data plane be supported. It also requires that static provisioning of LSPs and services be possible, meaning you don't have to have the routing protocols and the dynamic control plane present to be able to provision and build your services and LSPs. It has to be capable of forwarding data and taking recovery actions whether or not the control plane and management plane are present. So this means in the event of a network failure, it must be possible and able to recover that failure and to keep on operating without having to have a control or management plane intervene. So a routing protocol shouldn't be needed to help these MPLS-TP services recover in the times of failure. This statement refers to the requirements to supporting rings with protection and recovery mechanisms, again, specific to MPLS-TP. Transportation of MPLS-TP transport paths. This point describes how MPLS-TP LSPs must be able to be transported over other server layer networks. This would include other MPLS-TP infrastructures, Ethernet, SONET SDH, or OTN. So again, because MPLS itself is agnostic to the transport, MPLS-TP also takes on some of those features, but they require that the LSPs are able to go over MPLS-TP itself, as well as Ethernet, SONET SDH, and OTN. MPLS-TP requires that there are mechanisms to ensure the integrity of transported customer service traffic, as required by the SLA service level agreement of that service. This means that there must be something present to be able to monitor and assure that the service is getting the performance and connectivity that is required by the stated SLAs. Data plane forwarding has to operate on the MPLS label just like MPLS forwarding does already, but now they're adding 1+1 and 1-to-1 protection with revertive and non-revertive behavior. So this is where ring protection comes in, on the 1+1 and the ability to fail over from the primary path to a secondary path. Well, with 1+1, you have traffic going down both sides of the network already, which means you're much faster failover, and what that means is you're going to select one side to receive the traffic on, one side to have as the active side, and because you can't receive duplicated traffic at the destination, you have to have some kind of a selection mechanism. What this says for revertive and non-revertive with 1+1 is you have to have some way of having a selection mechanism either go back to its original state or leave it in its new state. 1-to-N is your ability to have your primary path carrying traffic and have the secondary, tertiary, quaternary paths available for switching in the event of a failure of the primary path. Now, the ability to switch back to that primary path when it is repaired is called revertive, whereas staying off the primary would be non-revertive. These features are required in MPLS-TP. The final feature is that MPLS-TP requires OEM-based and management plane recovery triggers. Notice that the control plane is not here, because control plane and management plane must be physically separate and reversion must not depend on the control plane for that recovery. So in this case, it would be using BFD for detection of the failure. For example, BFD heartbeats would be used to identify path-based failures as opposed to immediate link-based failures, and the speed of recovery depends on how fast your heartbeat interval is for BFD. Management plane means whatever management capabilities you have that would be able to intervene to assist with the recovery as well. When you summarize all the points on this screen, you'll see that 1+1 transport with OEM triggers does result in an always available service. In this slide, we'll review the OEM specific requirements of MPLS-TP. These are stated in RFC 5860. RFC 5860 states that the protocol solutions for OEM must support the capability to be concurrently and independently operated end-to-end and on segments. OEM functions used on any individual pseudowire, LSP, or segment should be independent of the OEM functions used on a different pseudowire, LSP, or segment. This means that events and measurements taken on one LSP, for example, are not to be affected by events or measurements of another LSP. OEM packets for a specific pseudowire, LSP, or segment must follow the same exact path as user traffic for that pseudowire, LSP, or segment. This is called fate sharing. So for example, when you're running BFD, bidirectional fault detection, delay measurement, or loss measurement, these packets used for these measurement tools, the OEM packets, must be fate shared with the pseudowire, LSP, or whatever it is that you're using those packets to monitor. This last statement basically says the feature capabilities of your OEM toolset has to have the ability to enable diagnostic tests on a pseudowire, LSP, or segment. So loopback would be one of the example of this capability for this tool set. The key feature emphasized in the OEM requirements for 5860 is in-band OEM. What this means is you have now got service-specific fault detection and recovery. It's not something that's generalized. It's not something that's approximated. This is now OEM that can be tied to each individual service, LSP, or segment of an LSP. Let's do a quick review of the highlights of additional capabilities of MPLS-TP over MPLS. There's no control plane required for MPLS-TP. This allows fast reconvergence. Forwarding of packets in MPLS-TP is independent of IP. It doesn't get involved with complex routing and control protocols. You don't have OSPF, ISIS, or RSVP in MPLS-TP. Static LSP provisioning and optional use of the dynamic control plane is available in MPLS-TP. So that means that you are required to be able to statically define LSPs, but you're allowed to use routing protocols if you really want to. OEM features from Sonnet SDH for failure detection and action are available in MPLS-TP. This means things like OEM, fate shared with the services and LSPs and pseudowires that are being monitored, as well as OEM triggered protection switching. MPLS-TP physically separates the management and control planes from the data plane. Packet forwarding continues in the absence of the control plane. In MPLS-TP, bidirectional support is introduced. This offers path symmetry, so you can now use bidirectional co-routed definitions of an LSP to ensure that the path out is the same as the path back. MPLS-TP supports both multicast LSPs and pseudowires. MPLS-TP also explicitly supports ring topologies. This reduces network complexities. MPLS-TP requires connection-oriented. It does not allow connectionless. You cannot have more than one choice for how to get from A to B. You always know where your traffic is going. It's deterministic. The telecommunications industry is racing forward trying to implement these new flavors of MPLS. As MPLS-TP is achieved by more and more vendors, are you sure that your critical network requirements are covered in a carrier, enterprise, or utility world? In other words, can a carrier MPLS-TP solution meet the needs of utilities? Major vendors today are focused on carrier environments and enterprise corporate environments. Some of these vendors have made very subtle additions to the base functionality of already deployed versions of IP-MPLS in order to say they are meeting the standards. This is true for cases like BFD for OEM. How is that BFD session defined to be associated with the specific pseudowire or the LSP? Is it done in hardware? Or is it done in software? The 50 millisecond recovery target that everyone's talking about in the carrier-based world, it really is a glass floor. Why is 50 milliseconds the limitation? Software versus hardware approach to survivability. Is the problem to getting your network to be recoverable? Is the approach you're taking using hardware and hardware design where things are much faster? Or is it done by adding more software on top of existing layers of hardware and software? Do you need to transport clock and clock domains across your network? If you have the requirement to extend your clock domains, does this mean you need to buy more hardware? Is synchronous Ethernet and precision time protocol supported? What do you need to do to maintain a synchronous Ethernet or a clocking domain across your network? So what they've designed for MPLS-TP as a standard, it's great. And how carriers and enterprise environments are making use of it all, it's good and dandy, but what is important to a utility? Utilities have much tighter and critical infrastructure that they need to support. Well, what that means is you want to make sure that whatever solution you have has deterministic performance and utility-grade quality of service. For example, the JPAX uses tightly controlled protection switching. You want to make sure that these events of path or link failure are detected in a very small amount of time. With the JPAX, for example, it can detect a path failure using BFD within as little as 10 milliseconds or smaller, depending on the number of heartbeats you want to configure. With loss of signal, LOS, it will catch that failure in 3 milliseconds. You want to have a very, very short recovery time. On top of that, you want to minimize your end-to-end service latency. On JPAX, it's done within about 4 milliseconds. Converged TDM and Ethernet service planes, you don't want to buy different boxes to do all these different things and then have all the complexity of bringing them all together. You want your solution to be able to handle both TDM and Ethernet services and applications all in one platform. For whatever solution you choose, you want to make sure that it's got a really good, tight, strong alignment with your relay vendor because it's supporting your most critical applications. This is the environment you're trying to address as a utility. Whatever box you're putting in the network, it would be awesome if that could really understand and work well with the equipment you're putting into your application environment. Of course, it needs to be scalable, not just OSI scalable, being able to handle things like your physical, your layer 2, 3, and all the way up to layer 7, and really understanding all the applications at an application level, but also horizontally. You want to make sure the modularity in what you're able to do with this box is very flexible to be able to do and handle all the services you want to throw at it. Also critical to utility customer environments, the gear and the solution you purchase needs to be industrially hardened. It's going to be installed into harsh environments, and critical equipment within that needs to be redundant. You need to make sure that you have full redundancy so that you don't lose service in the times when you really need to have it. It needs to be AAA secured in order to be compliant with NERC and NIST. Being built on open standards and supporting interoperability and full management allows you to have mid-vendor meets and a flexible network topology. Simplification of your NMS and having standard northbound management interfaces allows a consistent, flexible, and powerful way of managing your infrastructure. In this final chapter, we will introduce you to the enhancements made on the JunglePAX for MPLS-TP. We like to call it MPLS-TP squared. We will review OEM, Operations, Admin and Management, the hardware, and EMS NMS, where we manage both the node and the network on the box. GE's JunglePAX Platform is a platform that runs MPLS-TP. As we mentioned earlier though, the MPLS-TP we've implemented on the JunglePAX is an enhanced version of MPLS-TP. We don't just meet the standards, we beat them, and we like to call that MPLS-TP squared. The JunglePAX is designed specifically for network operations requiring mission-critical and time-sensitive communications within harsh substation environments. The JunglePAX runs an optimized version of MPLS-TP that provides determinism for secure and dependable packet transport. It's built on a synchronous Ethernet heartbeat like Sonnet. The JunglePAX is a transport quality multiplexer that converges PDH, TDM, Ethernet, and IP-based traffic over a connection-oriented next-generation MPLS-TP fiber optic network. Another important feature of the MPLS-TP squared offering on GE's JunglePAX is its active working and protection hardware paths. True 1+1, which give fast line protection switching under 10 milliseconds, and it's all done completely independent of the control plane. The important thing to remember with GE's 1+1 protection is that it's receive selected, not source selected. So the end that is in control of determining which of the 1+1 paths to listen to is the destination. This results in very, very fast failover times. And it's also really important to remember that this is fully revertive. Part of the OEM that is supported under GE's MPLS-TP squared offering is BFD triggered protection switching. So this means not only link detection for loss of signal, but BFD, bidirectional fault detection, is used to protection switch between working and protect paths. On GE's JunglePAX, it supports 256 sessions, BFD sessions in hardware today. With a 3.3 millisecond heartbeat and 3 heartbeat loss detection default, 10 millisecond detection periods are guaranteed. You can set the number of heartbeats you want to wait for lower. It just means that you need to make sure you're comfortable and familiar with the level of reliability of your transport. So whatever plant you're using for your wide area, be it optical or etc., you want to make sure that you don't lose heartbeats and give yourself any false positives. As I mentioned earlier, with the default of 3 times 3.3 milliseconds, this means that you get your 9.9 milliseconds of detection. However, if you need shorter detection times, you're able to drop the number of heartbeats you're waiting for. Now with JunglePAX MPLS-TP, OEM is supported for underlying infrastructure and service-based performance and availability management. What that means is BFD is offered to detect path and service connectivity at both the LSP and pseudowire level, but also you can then associate the delay measurement and loss measurement capabilities with specific LSPs or services. Again, this is a feature of MPLS-TP that is not available in standard IP MPLS. So you can have true fate shared measurement of what's going on in your network. GE's JunglePAX doesn't just support MPLS-TP in software. GE's JunglePAX is actually designed in hardware to be tailored to supporting the MPLS-TP environment. Customized hardware results in very, very low end-to-end system latency. Clocking features are incorporated into the GE JunglePAX solution to facilitate clock signaling extended across MPLS-TP infrastructure utilizing both built-in synchronous Ethernet and RFC 1588 capabilities. There's a flexible mix of PDH, TDM, and SONET SDH interfaces on the JunglePAX. GE's JunglePAX is fully hardware redundant. This means the 1+1 support of active working and protect paths is supported in such a way that there is no single point of failure, hardware or software-wise, anywhere in the JunglePAX. Of course, with the GE JunglePAX being aimed at the utility market, and GE's close ties to that market, it supports IEEE 1613 and IEC 61850-3. Completing the rich set of features brought to MPLS-TP² through GE JunglePAX is EMS/NMS features embedded on the JunglePAX itself. Element management services on the JunglePAX actually involves management of not just the JunglePAX node itself, but the collection of nodes forming the JunglePAX network. The NMS and EMS capabilities on the JunglePAX allows self-discovery and automated discovery of every JunglePAX node in the network, such that you can get a full network view and status awareness of what's happening in the JunglePAX network automatically and in real time. This EMS allows static provisioning of not only working and protect paths through your network, but also provisioning of all of your services, VPWS, VPLS, and VRF. Adding of manual provisioning and switching capability to alternate paths in the management plane is available through automated capabilities. If you think about it, with an EMS embedded in the JunglePAX and the programmatic and software capabilities that come with that, this allows us to leverage extensive event-driven programmatic responses to a wide array of network events, and these capabilities are resident in both the JunglePAX and the GE NMS. Integrating the NMS into hardware optimizes information collection and real-time event response. This is all based on predefined fault correction scripting. By integrating GE's NMS into JunglePAX, this enables extension to substation services to incorporate the Industrial Internet 2.0. It also allows full reliability reporting to help you with NERC compliance. In addition, of course, there's all the embedded capabilities of MPLS-TP, and the combination of that with GE's EMS, you can now have performance monitoring and trending that was not so easily done in the past. It required multiple sets of software or platforms to collect all the information and be able to bring it all together using one consistent method. This is now possible through GE's NMS using performance monitoring and trending. Let's summarize the key strengths brought to the market by GE's JunglePAX MPLS-TP² services. We start off with tight control over protection switching. This employs clock signaling extended across MPLS-TP infrastructure utilizing built-in SYNC and RFC 1588 capabilities. GE JunglePAX hardware is fully redundant with custom hardware offering 1+1 protection for fast line protection switching, under 10 milliseconds, and all independent of the control plane. BFD triggered protection switching between working and protect paths is a key feature of this MPLS-TP solution. Of course, with the JunglePAX being built for utility markets, it is designed to operate within the harsh utility environment with full support for IEEE 1613 and IEC 61850-3. The JunglePAX supports a flexible mix of all service types. This means it is purpose-built for utility-critical communication networks. GE's JunglePAX is quality in a packet world and is built for IT and OT needs. Thank you for watching this MPLS Part 2 module in the overall training series related to GE's JunglePAX Converged Communications Platform, designed with purpose for utilities. In this video, we provided a foundational understanding of the differences between IP-MPLS and MPLS-TP. We've carefully laid out the strong benefits of MPLS-TP and its alignment with the needs of stringent networking environments like that of the power utility sector.